In 2026, humanity is preparing to return to the moon for the first time in half a century. The last crewed lunar landing took place in 1972 with Apollo 17. Now, at this very moment, the long-awaited return of human spaceflight to the moon after 54 years is about to happen. What NASA envisions is not a short-term one-off mission, but a grand plan to build a second sphere of human activity on the moon over several decades. Why now? And why return to the moon? Let us unravel the full picture of the Artemis program. The decisive difference from the Apollo program lies in perspective, short-term versus long-term. During the Cold War, the United States and the Soviet Union rushed toward lunar landings as a means of demonstrating national power. In contrast, the Artemis program aims to maximize economic and scientific outcomes. By constructing a base that enables long-term habitation on the lunar surface, humanity will expand its living and economic spheres from Earth to the moon. The first historic mission, Artemis 1, was carried out in November 2022. It was an uncrewed test flight designed to verify whether NASA's latest systems could safely carry humans on a round trip between Earth and the moon. These systems are the Orion Crew spacecraft and the Space Launch System, or SLS rocket. Orion is the only spacecraft capable of carrying astronauts rapidly to the moon. The living space for the crew is called the Crew Module, which can accommodate up to 4 astronauts for as long as 21 days. Below it is the Service Module, which generates electrical power and propulsion. It also supplies oxygen and water necessary for survival, making it the lifeline of the spacecraft. At the tip of the spacecraft is the Launch Abort System, designed for emergencies. If a serious problem occurs during descent, Orion can be separated from the rockets and land safely in the ocean. The massive rocket that launches Orion is the SLS. It stands 98 meters tall, and its liftoff mass is about 2,607 metric tons. In both size and performance, it far surpasses any rocket currently in operation. The configuration used for Artemis 1 can transport up to 27 tons of payload to a distance of 380,000 kilometers. It is the only rocket capable of sending Orion, astronauts, and cargo to the moon in a single launch. The Artemis 1 mission lasted 25.5 days. It took 5 days to reach the moon after departing Earth orbit, followed by about 6 days in lunar orbit. Then, Orion approached to within roughly 130 kilometers of the lunar surface and returned to Earth using the moon's gravity. The spacecraft traveled as far as approximately 432,000 kilometers from Earth, setting a new record for the farthest distance ever reached by a human-rated spacecraft. Cameras mounted on Orion's solar panels captured scenes throughout the flight. It was the first time since Apollo 17 that the moon had been photographed from such close range. This footage shows Orion re-entering Earth's atmosphere. As the spacecraft compresses the air ahead of it at extreme speed, the energy is converted into heat. During re-entry, Orion was traveling at 11 kilometers per second, and its temperature rose to about 5,000 degrees Celsius, yet it withstood this intense heat. After passing through the atmosphere, Orion deployed its parachutes and splashed down in the Pacific Ocean off the coast of California. As a result, Artemis 1 concluded with great success. According to NASA's analysis, Orion achieved all 161 test objectives. Furthermore, the service module generated 20% more power than expected while consuming 25% less, demonstrating performance beyond expectations. Following the uncrewed flight test of Artemis 1, the next mission is the crewed flight, Artemis 2. Its primary objective is to demonstrate that Orion can function properly with astronauts aboard in deep space. Artemis 2 will not land on the moon, but will fly around its far side before returning to Earth. First, the SLS rocket launches Orion and inserts it into Earth orbit while discarding unnecessary components. Next, Orion and the rocket's upper stage, called the ICPS, complete 2 orbits around Earth. The reason they do not head directly toward the moon is to verify that all systems operate normally while orbiting Earth. Then, the ICPS fires again to push Orion into a more distant elliptical orbit, accelerating it to the speed necessary for lunar transfer. After this maneuver is completed, the ICPS separates from Orion, but its role is not yet over. Orion temporarily switches to manual control, repeatedly approaching and departing from the separated ICPS. This procedure allows astronauts to practice the docking maneuvers required for future lunar lander operations in lunar orbit. After completing this training, Orion returns to autonomous mode and ignites its engines towards the moon. From there, it takes about 4 days to reach lunar vicinity. This footage simulates the view the Artemis 2 crew will see on the day they come closest to the moon. Their distance from the lunar surface will range from about 6,400 to 9,700 kilometers. Flying around the far side using the moon's gravity, they will lose communication with Earth for 30 to 50 minutes. Although the moon's far side appears brightly illuminated in this simulation, the actual view may differ significantly depending on solar illumination conditions. For example, if Artemis 2 is launched in early February, most of the far side will be illuminated. But if the launch is delayed, the illuminated area will shrink. During the Apollo missions, the far side was dark and the near side was illuminated, allowing astronauts to land in daylight. After looping around the far side, Orion is naturally captured by Earth's gravity and returns without using propulsion. As it approaches Earth, the service module separates and only the crew module re-enters the atmosphere. It then deploys parachutes and splashes down in the Pacific Ocean, concluding the mission. Although the entire mission lasts only 10 days, it represents the first human spaceflight beyond low orbit in the 21st century. Artemis 2 is also significant because it marks humanity's first departure beyond Earth's magnetic field in half a century. The most serious health risk of human spaceflight is cosmic radiation. Normally, Earth's magnetic field blocks most of it, so the impact on humans is minimal. However, outside this protective shield, radiation levels rise to life-threatening levels. High-energy particles pierce the human body like bullets, causing immune system disruption, cognitive impairment, cataracts, and, in the long term, increased cancer risk. Beyond the magnetosphere, the environment is extremely harsh for humans. There are 3 primary sources of space radiation. First, galactic cosmic rays originating outside the solar system. Second, solar energetic particles generated by solar flares. Third, the Van Allen radiation belts, regions of high-energy particles encircling Earth. The inner belt consists mainly of particles produced by interaction between cosmic radiation and Earth's atmosphere, while the outer belt is composed of solar particles trapped by Earth's magnetic field. Orion must pass through these regions, raising the question of how much radiation exposure the crew will experience. Radiation dose is measured in sieverts. On the International Space Station, orbiting at about 400 kilometers, astronauts receive an average daily dose of about 1 millisieverts, roughly equivalent to the radiation we receive on Earth over 6 months to 1 year. Even so, this is more than 100 times the radiation exposure on the ground. The expected radiation dose for Artemis 2 is estimated to be comparable to a full-body CT scan over 10 days. NASA believes that for short-duration missions, health risks can be kept to a minimum. In the event of a sudden solar flare, astronauts will shelter in a specially shielded area inside the spacecraft. However, during future long-term stays on the Moon or Mars, radiation risks will increase to potentially lethal levels. How can radiation exposure be reduced during months or even years in deep space? Artemis 2 aims to provide clues to this challenge. Why, then, is humanity returning to the Moon now? With the end of the Cold War, the original motivation seemed to have vanished. Yet, in the 21st century, the importance of the Moon has only grown as scientific, economic, technological, and international objectives converge there. First is science. While Apollo mainly explored regions near the lunar equator, Artemis focuses on the South Pole, where permanently shadowed regions may harbor frozen water. In space, water is an extremely valuable resource, essential for drinking, sanitation, oxygen production, and even rocket fuel when split into hydrogen and oxygen. Another promising resource is helium-3, a rare isotope of helium. Some market surveys reported prices as high as $19 million per kilogram in 2024. Helium-3 is a byproduct of nuclear fusion in the Sun and arrives on solar wind particles. Because Earth's magnetic field and atmosphere block most of the solar wind, helium-3 is scarce on Earth. But on the Moon, it is thought to have accumulated in the soil over billions of years. Its greatest potential lies in its possible use as fuel for future nuclear fusion power, which could provide vast amounts of clean energy. Second is economics. Resources like water and helium-3 represent enormous economic potential. Whereas past space exploration was conducted solely by governments, private companies now play an expanding role. They provide transportation, supply, and communication services, which NASA purchases, transforming space development into a sustainable market. Third is technology. The long-term goal of space exploration is human settlement on Mars. The Moon offers an ideal testing ground, allowing humanity to develop life support systems, radiation protection, logistics, and operational techniques under manageable conditions. Fourth is international cooperation. The Artemis program exceeds the scale any single nation can achieve alone, involving partners from Europe, Japan, and Canada. In today's tense global climate, strengthening peaceful collaboration in space is more important than ever. Artemis is not merely a remake of Apollo. It is the first step in a grand roadmap toward Mars. The Moon's resources, its role as a testing ground, the creation of a space economy, and international cooperation all make it central to humanity's expansion into space. Artemis 2 is only the beginning. Half a century after the last lunar landing, humanity stands at a turning point that will shape the future of space exploration.